Let us begin with a word of prayer. I will start. Dearly Father, we thank you for this day. Again, Lord, I thank you for the students and this time we have together. I'm going to pray for the people who've lost their houses to tornadoes locally, that you just find them the help that they need, and that the churches around could reach out to those people, Lord. In your name I pray. Amen. All right, so let's talk about orthonormality. Orthonormality of a set. What's that mean? So, definition, if we have V paired with inner product, right? And inner product space, then V1, V2, N is orthonormal if when we take the inner product of Vi with Vj, we get Kronecker delta Ij, right? Which you will remember is 1 if I equals to j, and it's 0 if I is not equal to j, right? So this is what orthonormal means. A set is orthonormal if it satisfies this condition. So just to unwrap it again, what this means then in detail is this means that Vi, Vj is equal to 0 for I not equal to j. And that condition alone gives us orthogonality of this set. Let me call it S. All right, so orthogonality is that. The normality, right, the normality has to do with the fact that the inner product of Vi and Vi is equal to 1, right? But by definition, this is the induced norm of Vi squared, right? So the case I equals to j tells me that, in fact, the length of each vector in an orthonormal set is 1. So each vector in an orthonormal set is what's called a unit vector. Another way to look at this is if you're given an orthogonal set, you could normalize each vector and turn it into a orthonormal set. So here's an example of that. Kind of low example. If I had S equal to the set containing 1, 1, 1, 1, and then 1, minus 1, 0, 0, and 0, 0, 1, minus 1, you can check that this is an orthogonal set. All right? So this is orthogonal with respect to, inner product of A and B being the trace of A, B transpose, right? In particular, the inner product of 1, 1, 1, 1 with 1, minus 1, 0, 0, and the inner product of 1, 1, 1, 1 with 0, 0, 1, minus 1, and the inner product of 1, minus 1, 0, 0 with 0, 0, 1. These are all the possible distinct pairings, right? The first with the third, the first with the second, and the second with the third. Those are the possible distinct pairs. And the inner product here is what? 1 minus 1 plus 0 plus 0. Here you got 0 plus 0 plus 1 minus 1. Here you've got 0 plus 0 plus 0 plus 0. Anyway, however you slice it, 0, 0, 0. So all the possible inner products of these three matrices are 0, which proves that this is an orthogonal set. But it's not normal, right? This is not a normalized set. What's the length? What's the length of 1, 1, 1, 1? It's the square root of 4. 1 plus 1 plus 1 plus 1, right? Anyway, so the length of that one's 2. The length of 1 minus 1, 0, 0 is the square root of 2. And of course, that's also the length of 0, 0, 1, minus 1. How am I calculating the length here, guys? Remember that the length of a vector, x, is generally speaking the square root of the inner product of x with itself, right? This is how we defined the induced norm for V, right? So here's this set S, right? How can we normalize S? How can we find a normalization of S? Use following technique, right? Any vector x not equal to 0 has x hat, right? 1 over the length of x times x as a unit vector. Let's prove that. Calculate what's the length of x hat. What's x hat with x hat like this, right? By definition, that's 1 over length of x, x, 1 over length of x, x, right? So this up here is a definition. The unit vector in the x direction, normalization of x if you like. Then properties of inner product, what? We pull the scalar out of the first entry, we pull the complex conjugate of the scalar out of the second entry. Right? But the thing is, this by construction is an element of 0 to infinity. So the norm is a non-negative real number. Whether or not we're in a real or a complex vector space, the norm is real. So what that means is that I can pull both of these scalars out. They're both real numbers. And so I can pull it out to the norm of x squared, inner product of x with x, which is what? Inner product of x squared divided by the inner product of x squared, otherwise known as 1. Right? So you can take any non-zero vector and you can divide by its length and make it into a unit vector. So we can apply this procedure to my set S and turn it into an orthonormal set. So an orthonormal set, let's say T, with the span of T equal to the span of S, is easily obtained. What is it? T equals to, I'll start us out, 1/2, 1, 1, 1, 1, then what? This had length what? Square root of 2, right? So we do 1 over the square root of 2, 1 minus 1, 0, 0, and then 1 over the square root of 2, 0, 0, 1 minus 1. All right. So if we're already given an orthogonal set, it's pretty easy to obtain an orthonormal set, provided that there's not the 0 vector in there, right? If there's 0 vectors in there, we're in trouble. We can't normalize the 0 vector, right? Because this formula right here for x hat, it doesn't make sense when x is equal to 0, right? If x is equal to 0, we'd have division by 0 in that formula. Any questions? What it is? A question?
Yeah, why isn't the first, why is it, oh, never mind, I get it.
It's because the length is the square root of 4, which works out to 2 as it happens, yeah. All right, so here's a beautiful result, theorem. If beta, v1, v2, vn, is an orthonormal basis, for V, then the coordinate vector of x with respect to the beta basis equals to blank. So we'll fill in the blank in our proof, all right? Let's figure it out. So here's the proof. Suppose x is equal to c1v1 plus c2v2, plus cnvn, right? In other words, we have the summation I equals 1 to n of ci vi, where I'm assuming that the v1 through vn forms an orthonormal basis, all right? Let's calculate the inner product of, let's say, x with v sub j, right? Well, that would be the inner product of the sum I equals 1 to n of ci vi with vj, right? But by properties, in fact, by the definition of inner product, we can pull out the sum, and we can pull out the scalar in the first entry by assumption, right? By the linearity of the first slot. And what does that give us? Well, that gives us the sum I equals 1 to n of ci with vi comma vj, right? But by assumption of orthonormality, this is just what? Kronecker delta ij. What happens when we take the sum over Kronecker delta ij? The sum vanishes, right? Everything non-zero, the only non-zero term is when I is equal to j, right? Where here j is a fixed but arbitrary index. So what does that simplify to? Just cj, right? This simplifies simply to cj, right? And so we can go back up in here, and you can tell me what is the first component. It's just x with v1, right? What's the second component? It's the inner product of x with v2, right? And so forth. The nth component is the inner product of x with vn. So what I'm telling you is, with respect to an orthonormal basis, if you want to calculate the coordinate vector of a given vector, all you have to do is take the inner product with the basis. That's really, really nice. So this is an important theorem for us going forward. Another theorem that we have is that if beta is orthonormal basis for inner product space V, right? And x, equals to, let's say, x1 v1 plus x2 v2 plus plus xn vn, then using the norm of x equal to the square root of the inner product with x and x as usual, right? Just reminding you, that's the definition. We find that the length of x squared is equal to x1 squared plus x2 squared plus plus xn squared. So the length of a vector squared with respect to an orthonormal basis is the sum of the squares of the components. That says an orthonormal basis pretty much works like the standard basis that you've seen in Calculus 3, right? Like if we calculate the length of a vector, take the square root of the sums of the squares, that gives you the length of the vector. Well, this says that the same thing is true for an orthonormal basis in the abstract. How would you prove this? Well, let's see here. N equals to 1, we got what? X is equal to x1 v1, so the length of x is equal to the length of x1 v1, which is squared, right? So that's the absolute value of x1 squared, well, modulus of x1 squared, generally speaking, v1 squared, but we're assuming that v1 is a unit vector, so this just gives us the modulus of x1 squared. Oh, and I see I have made a mistake. What am I assuming when I write this? I'm actually assuming we're working with a real vector space when I write that. So if you wanted to allow for the complex case, I should really replace this with moduli. You can drop if the field is the reals. So, I mean, there's n equals 1. If we assume, well, let me just work out n equals 2 instead of n equals 2. So suppose you've got, v1, v2, orthonormal basis for n equals 2-dimensional vector space, right? Well, I'm getting dragged into something I don't really want to get into. I don't really care about the basis statement here. I just want to suppose that you've got an orthonormal. I'm not interested in the basis aspect of this argument. I just want to say if you've got a set of n vectors which are orthonormal, let's drop the basis, yeah? I mean, in this context, right? Fine. So I'm not committing to it being a basis for the sake of this argument. So my point is, if you had one orthonormal vector, we get the formula. If you have two orthonormal vectors, well, work it out. So suppose we've got, v is equal to x1 v1 plus x2 v2. Then what's the inner product of v and v? Right? So you take the inner product of the vector with itself. That should give me the length of the vector squared. Right? So then what? Well, now we're all awake. Very good. So the point is, by distributivity, x1 bar with v1, v1, plus x1, x2 bar with v1, v2, plus x2, x1 bar with v2, v1, plus x2, x2 bar with v1, v2, v2. So here I'm using the sesquilinearity of the inner product, the fact that it's linear in the first slot and it's conjugate linear in the second slot. Sorry about that, but not really. I'll probably do it again. But my point to you guys is that this is 1, this is 0, this is 0 by assumed orthonormality, and this is 1, which leaves us with what? F's value of x1 squared plus the F's value of x2 squared, or as I said, it's really the modulus squared. And of course, the starting calculation was the length of v squared. So there's the proof for two vectors, and you could prove it for n by induction. If you assume it's true, assume the proposition's true for n, then you could look at n plus 1. That would be the sum of two things, and you just use the two-dimensional result paired with the induction step to prove that this holds for n things. So this is sometimes called the extended Pythagorean theorem for the obvious reason, right? Any questions about this? Now I had claimed for you guys that any any finite dimensional vector space can be made into an inner product space. Let's just pause and think about that for a second. How would you do it? Suppose you got a finite dimensional vector space. How would you define an inner product from the, you know, so, you know, we've got a finite dimensional vector space, right? So this is a construction. Suppose you've got V is the span over, you know, the reals or the complexes of beta. And let's keep it real for a second here, because, you know, if you can do it for the reals, you can do it for the complexes. And suppose beta is equal to V1, V2, Vn, right? So you want to define the inner product of x and y, right? Where let's say that those are given by the basis expansions, I equals 1 to n of x sub I, v sub I, and the sum j equals 1 to n of y sub j, v sub j. What would you, if you just wanted to guess, what would you say the formula should be for the inner product here? Again, I'm just saying it's an arbitrary vector space with a basis, 1 through n. No inner product happens to be given. I want you guys to make one up for me. So I need a formula, right? I need a formula which just involves the numbers, x sub i's and y sub j's. How about this? I equals 1 to n of x sub I, y sub I. That will actually work. This will define an inner product. In fact, in this inner product, you could say this. You could say basically I'm saying vi, vj is equal to Kronecker delta ij, and then extend bilinearly. And that would define an inner product, where I just assume that we have linearity in the first and second slots and also symmetry, since we're working in the real case. These formulas will in fact define an inner product. And what was the terms and conditions here? There were none. Just any finite dimensional vector space, you can give this as an inner product. Now what's the problem there? For a specific application, this formula may have little to do with the geometry you're interested in for the actual vector space, right? So on the ground, for an actual applied problem, this might not be a good idea. But at least in the abstract, we can always take a finite dimensional vector space and give it an inner product if we do so choose. And we can do it more so. We can give it an inner product such that a given basis becomes an orthonormal basis. Because that's what this construction does, is it makes beta an orthonormal basis with respect to this new inner product. So anyway, that's a fun construction, but usually that's not our context. Usually we're working in an inner product space where an inner product has already been given, right? So we have to work with what we're given and stay in that context, okay? So this is not a way to solve problems like I give you a set of vectors, you're like, I deem this set of linearly independent vectors to be orthonormal with respect to the inner product that I am so constructing. Haha, done. Like that is not enough. So we have to do these sorts of things, right? We're already given inner products, we have to work in it. That's my point. So here's a theorem. Given, you know, inner product space and a linearly independent subset S, subset of V, there exists, let's say S prime prime orthonormal, such that the span of S prime prime is equal to the span of S. the proof is via the Gramschmidt algorithm. Right. So what's this Gramschmidt algorithm? What on earth does that even mean? Let me show you how it works. So we'll begin with, our S, which is S1, S2, ... Let's suppose it's got k things in it. Right? So here's my S. It's linearly independent, right? So that means the vectors are non-zero. Yay. So step numero uno, let S1 prime prime equal to S1 hat. Where that's hat, the same hat that we introduced earlier. In a given system of measurement, this is a very painful hat to wear. It either means that you're going to have surgery to have your length elongated or compressed. So, not a hat you want to wear. Well, I guess you could wear shoes, right? I guess you could always wear some stilts or something. I don't know. The compression, though, that's harder. But the point is, we can normalize any vector by the length of the vector, right, times the vector again. So normalization, step number one. Step number two, we'll let S2 prime equal to S2 minus the inner product of S2 with S1 hat times S1 hat. This is also known as the projection in the S2 direction of, well, excuse me, I can't do math. This is actually the orthogonal, stink. This is S2 minus the projection into the S1 direction of S2. So what I'm doing is I'm subtracting off the piece of S2 which is in the S1 direction, and all that's left is a vector which is, well, perpendicular to S1 by construction. So you can prove this has the inner product of S2 prime and S1 hat equal to 0. It's also perpendicular to S1 itself as well, because S1 hat is a multiple of S1. So that's orthogonal, right? But then the trouble is that this S2 prime doesn't have to have unit length, right? So then you make S2, good grief, S2 prime prime equal to S2 prime hat. All right? Now you've got, if you're keeping a running total, you've got S2 prime prime and you've got S1 prime prime. These together make an orthonormal set. Your step 3 is to make S3 prime equal to S3 minus the projection onto the first, onto the second piece, S2, let's say S2 prime, S2, words. We want to calculate, if I could find my words today, S2 prime prime of S3 minus the projection onto S1 prime prime of S3. In other words, I'm subtracting off the part of S3, which is either in the S1 prime prime or the S2 prime prime directions. Specifically, the formula that I'm writing here is S3 prime is equal to S3 minus the inner product of S3 with S2 prime prime, S2 prime prime minus S3 with S1 prime prime, S1 prime prime. And this continues. All right. dot, 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 dot. Eventually, you get to the kth step, and there you'd have sk prime equals to sk minus the sum, I equals 1 to k minus 1 of s sub k with s sub k, well, s sub I rather, s sub I prime prime, s sub I prime prime. And then, of course, you form s sub k prime prime as the normalization of that. The resulting s1 prime prime, s2 prime prime, dot, 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 sk prime prime is orthonormal. And you can prove it has the same span. So this, in a nutshell, guys, is the Gramschmidt algorithm. It says that you start with a set of vectors and you just systematically orthonormalize it step by step using, well, you know, so this, I could put prime prime here. That wouldn't change anything. So what I sometimes call this is really orth s1 prime prime of s2. And in my way of thinking, the third one is actually, what you're actually looking at is, this is really the orth of s2 prime prime composed with the orth of s1 prime prime acting on s3. So you're, you know, basically the construction here is you're taking the orthogonal piece and then the orthogonal piece, and after you know, each application of the orth operator gets rid of everything which is parallel to the previous directions. So what you're left with is something which is not parallel to anything that you have up to that point. And you can prove that these orthogonal operators are linear operators, and so some of the things I'm not going to prove for you here today become easy to see from the composition of orth operators. Of course, you could also do some sort of induction argument, but anyway, this is Gramschmidt. Now, for an abstract, you know, for an abstract inner product space, I don't really know any way to do it calculationally except just to sort through this algorithm for the example, which is not that bad actually, by the way, guys, really not that bad. But if you have real vectors in, say, you know, Rn, R3, or R4 or something, there's actually a pretty decent website for just doing it for you. You can feed it the vectors and it will tell you what the Gramschmidt algorithm outputs for you. So that's nice. Yep.
For step 3, the first orth, is that an S sub 2 or S sub
2. You could do it in either order, though. Basically, all orth does is it says it takes the input and it subtracts off the inner product with the, like this would, if I put an S. Yeah, sorry about that. My point is that these actually commute, so it doesn't matter. Because all that operator is you take the vector and you subtract off the piece of the vector which is in the direction of either S1 prime prime or S2 prime prime. I should move on here. So theorem, let W be subspace of, you know, V with inner product, right? Then there exists an orthonormal basis for W. What's the proof? Pick, you know, beta tilde basis for W, then run the Gram-Schmidt algorithm on beta tilde to obtain beta orthonormal. So once you have this Gram-Schmidt algorithm, you can take a given basis, which doesn't have to be orthonormal. You run it, run the Gram-Schmidt algorithm, and you get an orthonormal basis. And they have the same span, so it's the same subspace. Right? Furthermore, theorem. Given W a subspace of V, well, oh, I'm sorry, I'm jumping the gun here a bit. If S is a subspace of V, it's not subspace, just a subset, then we define the perp to be X in V such that the inner product of X with S is equal to 0 for all S and S. Again, S doesn't have to be a subspace. It could be a finite set. But the interesting thing is you can prove that the perp, S perp, is a subspace, whether or not S is. So this is a definition theorem, which I think is a homework problem for you guys. S perp is a subspace of V. You can kind of see how that is if you take two things in the perp and you look at a linear combination of them by properties of the inner product, you're going to be able to satisfy the subspace test pretty easily, right? But there's more. Theorem, if W is a subspace of V, and, you know, V has inner product V, right? Then W perp is complementary. Subspace to W. Let me put that into more concrete terms. V is the direct sum of W and W perp. All right? Moreover, if beta equal to, let's say, W1, W2, Wk is orthonormal basis, for W, then we can define the projection operator onto W of X is just equal to the sum of, well, let's see here, X with, oh man, I wish I hadn't erased what I erased. I always, what was my formula for the jth component of the coordinate vector earlier on this lecture? Did I have X in the first spot or the second? The first. Okay, we're good then. So this is a generalization of the, so I talked about projection over there in the discussion of Gramschmidt. I'm talking about the projection onto like one coordinate, like the span of one vector. Now I'm introducing the notion of projection onto a subspace. So the projection onto a subspace we can build by just taking inner products with an orthonormal basis like this. And also we have orth W of X equal to X minus the projection, so that what? So the projection onto W plus the orthogonal projection onto W is straight up the identity on V. So the sum of these two operators gives you the identity on the whole vector space. But if I want to project onto a subspace, all I have to do is find a basis for the subspace, all right? And if I find a basis for the subspace that's orthonormal, I can use that to build a projection onto the subspace. Okay, so for a quick example, what about if we think about R2 by 2? I think that's the direct sum. Well, I mean, I know it's the direct sum of what? The 2 by 2 symmetrics and the 2 by 2 antisymmetrics. Are these, is the perp, I mean, I don't know. I'm not sure about this as I'm asking you guys. What is the perp of the 2 by 2 symmetrics? In other words, we're looking for, A in R2 by 2, right? Such that what? Such that the inner product of, where did my stupid definition go? Oh, it doesn't, this is real, so it doesn't matter. A with, with, well, let's say S is equal to 0 for S equal to S transpose, right? My suspicion is that that's the antisymmetric matrices, but I'm not sure right offhand, right? I mean, let's look at it. So what we got? We got A, B, C, D. That's my matrix, right? And I want the inner product with, let's say, X, Y, Z, Y, right? That's an arbitrary symmetric matrix, right? That's supposed to be equal to 0 for all X, Y, Z. So what is that actually? That's AX plus BY plus CY plus DZ equals to 0. Which gives me what? That gives me A plus B plus C, AX, right? And again, this is for all X, Y, Z, which is super nice. Why is that? If we have that this is true for all X, Y, Z in the reals, that means that we can pick particular X, Y, Z which suit our purposes, right? I mean, the only way that that can be 0 for all X and Y and Z is if the coefficients of X, Y, and Z separately vanish. Because we can put X equal to 1 and Y and Z 0. We could put X equal to 0, Y equal to 1, Z equal to 0. And of course, we could put X and Y both 0 and Z be 1. So you can see that the coefficients of X, Y, and Z have to separately vanish. Which is to say what? A equals 0, B plus C equals to 0, D equals to 0, right? Aha! In fact, this is the antisymmetric matrices, is it not? Because we just found that A has the form, 0, B minus B, 0. So this is the orthogonal complement to the 2 by 2 symmetric matrices is, in fact, as it happens, A2. Woohoo! So if I wanted to calculate the projection onto A2 of the matrix A, B, C, D, what would I get? So this is a kind of silly case. What's the basis for A2? One over the square root of 2, 0, 1, minus 1, 0 for basis, right? Orthonormal basis. And so if I was to calculate the projection onto the A2 subspace of an arbitrary 2 by 2 matrix, A, B, C, D, I would get A, B, C, D minus, the inner product of, well, A, B, C, D with this, I'm going to call this thing, oh, fine, I'll write it again. 1 over square root of 2, 0, 1, minus 1, 0. I can't fit it in. This thing again here, quote. So what you get is A, B, C, D minus 1/2 B minus C, 0, 1, minus 1, 0. What is that? We get a 1/2 of what? I think we got b plus c there, yeah? And down here, I believe we have 1/2 b plus c. I could be wrong about the other one. Is that right? I don't think it's right. What do we have in the lower spot? I've got c. Oh, I get minus. No, I'm sorry. I'm trying to. I got to think through this again. No, I was right before. All right. Anyway, I'm digressing. I'm bearing the lead here, you guys. So, beautiful theorems. We can find an orthonormal basis for a subspace by this Gramschmidt algorithm, right? We can build a projection onto a subspace like this. I'll show you guys next time that naturally leads to a solution of the least squares problem, like the problem of linear regression that you may be familiar with from statistics or whatever, right? It solves this closest vector problem. It's very interesting. But, you know, the thing I haven't talked enough about yet today, which is a shame, is just column vectors. How does this all work out for column vectors in the case we're just working with the usual Euclidean dot, the dot product? There we have the most beautiful formulas. So Rn paired with this guy is often called Euclidean space. So this is, I would often call this Euclidean n space, all right? Suppose you want to find the perp to a subset. Suppose you got S equal to S1, S2, Sk, a subset of Rn. You want to calculate S perp, what's that? You're looking for X in Rn such that what? X dot, well, rather S sub I dot X is equal to 0 for all S sub I in S, right? What is this, though? So this right here, guys, is nothing more than S sub I transpose X equals to 0, right? Which if we write it as a stack of things, we've got, S1 transpose X, S2 transpose X, Sk transpose X equal to 0. Put that all together, you've got S1 transpose, S2 transpose, Sk transpose times X equal to 0, combining it to one big matrix equation. Wait a minute. That's just to say that the matrix of S transpose times X is equal to 0. Right? I know we stopped talking about eigenvectors, but the null space is still with us. It looks like the null space is still important here. In fact, what is this? In other words, X is in the null space of what? The transpose of the matrix. So apparently we have the following theorem. The perp of S is the null space of the transpose of the matrix for S. So to calculate the perp of a subspace in Rn, all you got to do is take the vectors that span the given subspace, put them in a matrix, transpose it, calculate the null space. A basis for that null space is a basis for the perp. Then if you want to create an orthonormal basis, well, you still can do the Gramschmidt thing. But this is very nice, right? Because calculating orthogonal complements in the abstract, well, that kind of requires some thinking, right? Like I couldn't do that over here, could I? I actually had to work it out. But for vectors, column vectors, we have a straightforward calculational technique. Furthermore, what was the coordinate vector? One other thing, and I'll stop for today. You know, we had this formula, right? Phi beta of x equals to what was it? Beta inverse of x. Next time, I will prove for you that if beta is orthonormal, I know we don't have time today, but if beta is orthonormal, this is something I probably should have done today. Beta orthonormal, what does that mean? That means, actually, when you work it out, that beta transpose beta is equal to the identity. That's what orthonormality looks like as a matrix equation. What does that mean? That means that beta transpose is the matrix inverse. In fact, we could have derived that from the theorem I wrote earlier today, which was that to calculate the coordinates with respect to the inner product, we just take inner products, right? So what that means, if you track back to the coordinate vector, is that the formula for the coordinate vector formula for the basis on Rn is just multiplication by the transpose of the basis. Which do you prefer, inverting the basis or transposing it? I think transpose is the clear winner, right? But it comes at a cost. You got to have an orthonormal basis. Anyway, I shut up. Thanks.